Okay, in this video I want to talk about absolute value inequalities. Okay, let's just review absolute value quickly here. The absolute value of a real number is defined in the following way. It's defined piecewise. The absolute value of x is x if x is greater than or equal to 0. Okay, so non-negative. However, the absolute value of x is negative x if x is less than 0. In other words, if x is negative. Now, if x is negative here, and I put a negative sign out front of the negative, a double negative is positive, so that you can see the absolute value of any negative number is positive. Therefore, looking at this, you conclude that absolute value is always greater than or equal to 0, okay, for all real numbers. Here's another way of writing this, by the way. If x is greater than or equal to 0, then the absolute value of x is just x, so you don't do anything. If x is less than 0, negative in other words, then the absolute value of x is negative x, okay? Now, here's a geometric interpretation for the absolute value of x. The absolute value of x represents the distance from the origin, that is 0, to x on the real number line. You can see that I've got examples here on the real number line. Let's consider negative 3 here, okay? Negative 3 is 3 units from 0, therefore the absolute value of negative 3 is 3, okay? Here I've got units just because I have a unit distance measured off on the x-axis here. 2, the absolute value of 2 is 2 because 2 is exactly 2 units away from 0 on the real number line. By the way, the absolute value of 0 would have to be 0 under this interpretation also, because 0 is 0 units from 0 on the real number line. Now, we're mostly going to be considering inequalities in this video here, but just for review quickly, and this will be helpful, is to look at some equations involving absolute values first. Let's take this example. Solve absolute value of x is equal to 3. Now, when I say solve throughout, I mean find all real numbers that satisfy whatever the condition is, okay? Now, both negative 3 and 3 are 3 units from 0, from the origin. Therefore, there's 2 solutions to this, negative 3 and 3, which we write compactly this way, x equals plus or minus 3, okay? So think of it this way. You're at 0, you're going to move 3 units to the left, you would land at negative 3, or you could move 3 units to the right and land at 3, so those are the only 2 solutions there. Okay, let's look at a little more complicated equation involving absolute value. The absolute value of 2x minus 1 is 5. Now the first thing I'm going to do is note that the value 2x minus 1 must be plus or minus 5. Okay, this should be clear from the previous example where essentially right now I'm just thinking of replacing 3 by 5 here and x by 2x minus 1, and there we go. Okay, so there's actually 2 equations here. Okay, let's look at the first equation. I've got 2x minus 1 is negative 5. That implies by adding 1 on each side that 2x equals negative 4, so that x equals negative 2. On the other hand, I have this second possibility, 2x minus 1 equals 5. Adding 1 on each side, that would imply 2x equals 6, and then dividing both sides by 2, we get x equals 3. So there's 2 solutions here as well. X is equal to negative 2, or x is equal to 3. Now, notice that the solution in this case, these 2 values are not symmetrical about the origin or about 0 on the real number line, like what was true in the case up here. You can see negative 3 and 3 are symmetrical around the 0 there. And the reason for that is because I've got this subtract 1 here, okay? This is causing a shift in the solutions here, okay? That's causing a shift in the solutions. All right, that's not that vital. Let's look at some inequalities right now, okay? I'm going to start with the ones I think is a little easier first. I'm going to start where I'm taking the absolute value is less than or equal to a number, or the absolute value is less than or equal to a certain number, a real number. Okay, let's take this simple example here. You want to solve this. The absolute value of x is strictly less than 3. Okay, now let's think of our geometric interpretation here. Since the absolute value of x is the distance from x to 0, we're looking for all real x whose distance to 0 is strictly less than 3 units on the real number line. Then I come up here, I think about 0, okay, and I could move to the left, okay, and I could continue to move to the left, but I'm going to have to stop once I get to what? -3, because -3 is exactly 3 units from the origin, not less than 3, okay? And likewise, I could start at 0, that would be included, that's certainly less than 3 units from the origin, and I could move along to the right, but I would continue until I stopped at 3, okay, because 3 is 3 units from the origin, not less than 3 units, so I wouldn't be including 3 either. So you notice what I really have is all real numbers between -3 and 3, but not including the endpoints. And you notice that I have what? Open dots there at -3 and 3. So in set builder notation here, this is the set of all x such that, you remember that vertical bar represents such that. It's sort of dangerous in this situation with these absolute value signs looking so similar running around. I should have probably used colons there. But with this narration, I don't think we should get mixed up. Anyways, the set of all x such that absolute value of x is less than 3 is the same set, so it's equal to the set of all x such that x is between -3 and 3, or another way of saying that, -3 is less than x is less than 3. Okay, now if you remember from the previous video, how we could write this is in interval notation, right? We would have parentheses, -3, 3, okay? Parentheses because we are not including the endpoints of that interval. Okay, now let's look at a closely related problem. Absolute value of x is less than or equal to 3. Okay, for the solution, absolute value of x is less than or equal to 3 if and only if the absolute value of x is less than 3 or the absolute value of x equals 3. That's just slightly wordier than what I simply read off here, isn't it? Okay, now we already know from our previous problem just above that absolute value of x less than 3 is equivalent to saying x is between -3 and 3. And then we've got this or statement here. The absolute value of x is equal to 3. Remember, there's two solutions when we were dealing with those equations, actual equalities above. X equals plus or minus 3. Okay? Now, the set of all values that are between -3 and 3 or are actually equal to -3 or 3 is the set of all values between -3 and 3 inclusive. So in other words, I can just stick on equal signs on this like I've shown here, and I've got those real numbers for my solution. You remember the interval notation, we would end up using square brackets. So square bracket, -3, 3, square bracket. What we've effectively done up here when we included the equal sign in our problem is had a solution that ends up including the endpoints here. So I filled those in essence. Okay? All right, let's look at some sort of degenerate inequalities here, okay, involving absolute value and less than sign. Here I've got the absolute value and I've got less than, okay, and I've got 0 here, okay. Now let's look at the solution. There are no such x. Well, and the reason why is regardless of which value of x, real value of x I take, its absolute value is greater than or equal to 0. How could it possibly be less than 0 then? Well, it couldn't possibly be less than 0, so there are no solutions to this problem. Sometimes we would represent that by the empty set here. Notice that I've got those curly brackets or braces with nothing between them, okay? That's one way of writing the empty set. Another way of writing the empty set is sort of a 0 with a slash to it. It kind of looks like a Greek V there. This is actually what some people would call the null set. That's the same thing as the empty set. Null comes from the German meaning 0, actually. Okay? It means there's 0 elements in the set. Let's go ahead and look at a related problem here. Let's solve this. The absolute value of x is less than or equal to 0. Okay? Now, if you think about it, if you consider absolute value of x is less than 0, there was no solutions as we saw above. So the only possible solution left for this would be what? Absolute value of x equals 0. And the only number whose distance from the origin is 0 itself. So the only solution is x equals 0. Now, if you remember our interval notation for that, okay, square brackets to include the endpoints. For a single point, you would go what? Square bracket, the point, the square bracket, right? Or the number, I should say. Square bracket 0, 0, square bracket. That's sort of a long way of writing x equals 0. Okay, now this one is even easier here. Absolute value of x is less than -1. Again, there's no solution. That's even worse than this case up here, because here, remember the absolute value of x for all real x is greater than or equal to 0. How could it be less than a negative number? It couldn't. So no solution, so we write just the null set there. Okay? Here's going to be the rule. Okay? If p is greater than 0, so p stands for positive number. Okay? If the absolute value of x is less than p, this is true if and only if x lies between what? Negative p and p, or in other words, negative p is less than x is less than p. Okay, so we saw those above. And then a slight change here. Absolute value of x is less than or equal to p, okay, for positive p. If and only if negative p is less than or equal to x is less than or equal to p. Okay, so let's go ahead and apply this one last time to a simple problem here. Linear inequality. Okay, this is a linear function of x. Okay, just have a first power there. All right, the absolute value of 2x minus 1 is less than or equal to 5. Well, notice that our p here is 5, and that's greater than 0. So what we're going to do is rewrite this as a double inequality. Negative 5 is less than or equal to 2x minus 1 is less than or equal to 5. So I'm just applying this right up here. Okay. Alrighty. Now that's a double inequality, so we can work this pretty simply here because the x is in the middle and nowhere else. Okay, if you remember some of those inequalities we did in the last video, they could get a little more complicated. This one's easy though. Add 1 all the way through and we would have negative 4 is less than or equal to 2x is less than or equal to 6. And then divide by 2. 2 is positive, so the direction of the inequalities do not change. Negative 2 is less than or equal to x is less than or equal to 3. And then go ahead and put that in interval notation with the square brackets. Square bracket negative 2 comma 3 square bracket, and we're done. Okay, now let's talk about some inequalities. The students tend to find these slightly harder, but once they get used to them, they can do okay. These are inequalities where the absolute value is greater than or equal to a number or greater than a number. Okay, now let's go ahead and look at a simple example here. Let's solve this. The absolute value of x is greater than 1. Remember, we're looking for all real values that satisfy this. Okay, we'll look at this in terms of the geometry here for our solution. Since the absolute value of x is the distance from x to 0, we want all real x whose distance from 0 is strictly greater than 1 unit. Okay, so greater than 1 unit. All right, so think about that. So when finding such x, we need to move more than 1 unit from 0, or the origin if you like that word better. But it's from 0. But there's two ways you could move here. You could move to the left, or you could move to the right. Okay, so if I move 1 unit to the left, I would land at what? -1. But I have an open dot there because I have to move what? That's moving exactly 1 unit. I need to move more than that, but any movement I make further to the left from -1 will satisfy my condition. So I actually have all these numbers to the left, or less than -1, in other words, filled in. So this is all shaded in, as you can see. Okay? Open dot at -1, but everything to the left shaded in. Now likewise, I could have come over here to the right. If I had gone to the right instead, I would think about what? Stopping here at 1 and putting an open dot also, because 1 is 1 unit from 0. But if I move any further to the right, then I've got values of x that satisfy my condition that the distance from 0 has got to be greater than 1, so I shade this direction also. Okay, so notice that this solution set is actually disconnected geometrically. Unlike our previous example, right, where you had just a single interval, right, where we had the less than or equal to or less than, this solution set is disconnected. So we have two pieces that look like the real number line had a byte taken out of it. Okay? Now we do want to regard it as one set, so that makes us think of what? Union here. Okay? All right? So we're actually going to write this in interval notation as a union. But let's finish this here. Let's talk about the set builder notation. It's a set of all x such that absolute value of x is strictly greater than 1 is the same as we discovered, what? The set of all real x such that, what? X is less than -1, so that's the set of all those guys over there, or the set of all x that satisfy this condition, okay? X is greater than -1. Okay, so that's the right part of the solution here, okay? Now remember, that's an or symbol because we're finding the set of all x that satisfy this condition or satisfy this condition. Okay? One or the other. No x's, by the way, satisfy both of them, as you can see here. Now, in terms of interval notation, remember how this goes? You read from what? Left to right. So let's look at this set over here. We'd have parentheses, -infinity, comma, up to -1. Parentheses again, because we're not including -1. And then we want to have one big set out of this, right? So we got to have union. And then the right-hand part of the set here, we're starting at 1 and then increasing without end here. Okay, we're not going to include 1 though, so we need parentheses, 1 comma, infinity, and parentheses again, okay? Because there's no limit to the left or right. We've got to use -infinity and plus infinity there. Okay, I won't spend too much time on the second one. I sort of belabored the point in the previous example here. But if I go the set of all x such that absolute value of x is greater than or equal to 1, okay, there's my solution for what? The set of all x that is has absolute value strictly greater than 1, and all that would be left is the values of x whose absolute value is equal to 1, and that's what? Plus or minus 1, okay? So you would just throw in plus or minus 1 to this set, right? And you can see that would be equivalent to filling in these dots up here on the real number line, the -1 and 1. So our solution in terms of interval notation would be parentheses, -infinity, comma, -1, square bracket because we're including the -1, union, square bracket because we're including the 1, comma, infinity. Alrighty? Alright, I hope that made sense. Let's go ahead and solve a problem along these lines, okay? Let's talk about the solution to this problem. The absolute value of 3x plus 1 is greater than or equal to 7, alright? Now there's two possibilities. The 3x plus 1 could be less than or equal to -7, or it could be what? 3x plus 1 could be greater than 7. Okay, so it's similar to the situation I took up here, only x has been replaced by a little more complicated expression, 3x plus 1, but that doesn't matter. And it's going to be what? Greater than or equal to 7 instead of greater than or equal to 1. But this is essentially it. Notice if you think about this on the real number line, you've taken a big bite out of the middle. Okay, that's what happens with these. All right, 3x plus 1 is less than or equal to negative 7, or 3x plus 1 is greater than 7. You have to write it as two separate equations, right? I'm going to show that down below, a common error students make, but don't make it. All right, in just a minute here, let's solve for x. Subtract 1 on each side of the inequality, and I would have 3x is less than or equal to negative 8. Divide on both sides by 3. 3 is positive. The direction of the inequality does not change. X is less than or equal to negative 8/3. Over here, I perform similar operations. 3x is greater than or equal to 6, and then x is greater than or equal to 2. Now, if you take a look at these, you could graph these on the real number line or just think about them. I think you can see here that in interval notation, it would be from minus infinity out to minus 8/3. Use a square bracket because we've got this equal sign here. So we're including negative 8/3. Union, right? A square bracket because we're including 2 here. Okay. Out to infinity. Okay. So there's the solutions. Okay. In interval notation. Now, just a little warning up here. Now, let me circle this in here. You've got to write something like this to get the correct solution. Now, I've seen students do this before, and this is nonsense, where they'll take these two inequalities and they'll smash them together into a single inequality like this, or a double inequality without an or statement, okay? So it goes like this. Negative 7 is greater than or equal to 3x plus 1 is greater than or equal to 7. Do you see what the people did? How they just put these two together in a single line here. This is impossible because let me show you what this implies, okay? Notice, negative 7 is greater than or equal to this thing is greater than or equal to 7. That would mean what? This would imply that negative 7 is greater than or equal to 7. You see, following the inequality signs? Negative 7 is greater than or equal to 7. This is absurd. Okay? No. What this person tried to do was connect these two statements with an and statement right there instead of an or statement. If that had been an and statement, you could do this. You could actually put these together this way. Of course, there'd still be no solution. That would be absurd. But if that was an and statement, you could do that. All right? All right? So don't do this. I'm sorry you have to write out two separate equations separated by an or statement, but there's a lot more painful things in the world you have to do, okay, than this. It shouldn't be that big a deal. Okay, now let's go ahead and solve this. Again, we have some sort of borderline cases here also. Here I've got this problem. Solve. Absolute value of 3x plus 1 is greater than or equal to 0. Now I'm going to show you the solution here. I'm just change this into z for a second here. The absolute value of z is greater than or equal to 0 for all real z, right? Every single real number has an absolute value greater than or equal to 0. So the answer here, even if this is something fancy, would be what? All real numbers. I don't care which real number you put into that expression, 3x plus 1, you'll end up with a real number, and that real number will have an absolute value greater than or equal to 0. So the solution is what? All real numbers. Okay? Now, how do you write all real numbers in terms of interval notation? Okay, well, there's no limit to the left or right. Of course, you're not including minus infinity or infinity as part of the solution. You never do. Those aren't real numbers. But this is how you would write it. Parentheses, minus infinity, comma infinity, parentheses. Okay? That's all real numbers. Okay? All right, how about this one instead? This is related, but a little less trivial here. Solve the absolute value of 3x plus 1 is greater than 0. Okay? All right? Well, there's two possibilities. Okay? I'm going to treat it like I did this other problem up here. 3x plus 1 could be what? Less than 0, or 3x plus 1 could be greater than 0. Okay? Just so long as it's not equal to 0, okay, so long as that thing on the inside is not equal to 0, it'll have an absolute value which is positive, okay, which means greater than 0. So solve these two. Okay, subtract 1 on each side and divide. So we've got x is less than negative 1/3, or x is greater than negative 1/3. Now, all real numbers except negative 1/3 have the property of being less than negative 1/3 or greater than negative 1/3, right? Every real number besides negative 1/3 itself will satisfy one of these two conditions. So that this is equivalent to saying all real numbers except negative 1/3. So I wrote that x is not equal to negative 1/3. So imagine taking the real number line and just kicking out negative 1/3. So I drew an open dot there at negative 1/3 and shaded everything else in. Okay, that would be our solution. Okay, in interval notation, from minus infinity to minus 1/3, parentheses, right? Union, parentheses, negative 1/3 to infinity. Okay, this one, solve the absolute value of 3x plus 1 is greater than negative 5. Okay, this is easy too. The absolute value of z is greater than or equal to 0, which is certainly greater than 5 for all z. So once again, we have what? Just like the problem a couple problems ago here, we're going to have all real numbers as solution. Okay, so I don't care what real number I put in here. 3x plus 1 will also be a real number. Its absolute value will be greater than or equal to 0, and therefore greater than negative 5. So all real numbers. Here's the rule then that you want to remember, okay? If p is a positive number, so if p is greater than 0, okay? All right. In fact, if you want to, you could actually have that equal to 0 for this one. Absolute value of x is greater than p if and only if what? X is less than negative p or x is greater than p. Okay, so you want to remember that here. Now, absolute value of x is greater than or equal to p if and only if x is less than or equal to negative p or x is greater than or equal to p. So basically all we did was come up here and do what? Include the equal signs, okay? Because this only includes the extra values negative p and p, okay? So you want to remember this, okay? Have that memorized. And likewise, you want to remember this one, okay? Remember these two, and you should be good shape for these inequalities involving absolute values. Okay, well, I hope you understood that.